Welcome, and thank you for tuning in to learn about Portworx Data Services. While you're here, we'll talk about how Portworx Data Services, or PDS for short, can help your teams manage databases, and we'll go through some demos so you can see it in action. Let's jump right in. Once upon a time, we used to build monolithic apps. The full application might have been a typical three-tiered app with a web layer, application layer, and of course a database layer. Our web layer was load balanced to handle load, but all of our logic was stuffed into this app layer, which is where we'll focus today. If our application was some sort of online storefront, the app layer would have a bunch of services like a shopping cart service, an order or return service for people who were unhappy with their purchases, a search service, a promotion service to send ads to our users, and a recommendation service to suggest certain purchases for our customers. There are surely more than this, but I think these services give you kind of the idea. There are several problems that we would encounter when managing these monoliths. The first being that all these services might have been in a shared version control repository, but the application might be so big that there is a team of developers working on each of these individual services. This leads to conflicts when pushing data to the version control repo. A push from one team might make other services stop working, so these teams started fighting with each other and would have issues getting code updated with the shared code base they were working from. A second issue is that if the application needs to scale, we would need to scale the entire app layer. So if the search service, for example, needed more physical resources like CPU or memory, all of the services had to be scaled up as well, whether they needed more resources or not. This was pretty inefficient for us, and it made it trickier to see which service was using all the resources. And a third issue is that all of the services would need to share the same database in the database layer. This was okay, but many services would prefer to use a different type of data store. Maybe the cart service was very transactional and preferred a relational database model, while the promotions service might prefer a NoSQL database. We learned that if we could use a microservices-based architecture, we could get around many of these issues. Each service could be split into its own code base. This let us scale each individual service independently from the others, let developers work on each service separately and without merge conflicts, and also let each service choose what backing service they wanted to use for a database. We've seen an explosion of databases over the past several years. It's no longer a relational database from one of the big vendors. We can now use relational databases, NoSQL databases, graph databases, time series databases, document databases, and others. This really benefits the app because the service can choose the best solution for the task. However, think about the job of a database administrator or platform engineer trying to manage the details of this application. Do you suspect that when dev teams are ready to deploy this app, they open up tickets to deploy each of these databases? Can you imagine how long it would take to get 5 databases of different types set up and deployed so that our app will work? Even before that, we have 5 databases we'd need to set up, but in production, in QA, in development, in test environments, that's an awful lot of databases to manage. To make matters worse, we might be using different flavors of these databases if we use managed services from like cloud providers. MySQL could be a VM, it could be in containers, or it could be a managed database like Amazon RDS. You're quickly seeing that the management of these distributed databases can be quite challenging, and we haven't even talked about how you upgrade and scale these databases yet. This is what Portworx Data Services aims to solve. Developers looking to build a new app should be able to quickly get access to the components that make sense to them, and without having to stand in line for a service ticket to be fulfilled. Instead, Portworx Data Services offers sort of an online menu of data services that users can choose from. Just like a customer at a restaurant ordering a main dish and a side, PDS lets customers choose from a data service like MySQL and a side of high availability, if you'll allow me to take that analogy to its conclusion. We speed up the time to market of new apps, and then manage these databases after deployment. Hopefully at this point you get the idea and don't need more slideware for me to explain these concepts. Let's dive straight into a demo and we'll walk through how PDS can be used as a database store for your users. When you first log into the PDS portal, you'll see all the available data services that you can deploy to your Kubernetes clusters. We have Kafka brokers and RabbitMQ message buses, MongoDB Enterprise and Cassandra for NoSQL options, and we have MySQL and Postgres for relational databases, among others that I'm not going to mention. It's tempting to start with the deployments, but before you can deploy these databases to your Kubernetes clusters, we'll have to tell PDS which clusters you want to use PDS with. To do this, we look at deployment targets. To add a Kubernetes cluster as a deployment target, we need to look in the settings page. Here you can see I have a cluster already registered named PX Food Services. This is the cluster we'll use for our demos, and I've already registered it, but the process to register a new Kubernetes cluster is very simple. Click the Add Deployment Target button in the GUI, and you'll be presented with a Helm command to deploy the operator into the cluster. When you run this command in your Kubernetes cluster, it will deploy our operator, which reaches out to the PDS control plane to register the cluster with PDS and make it available for use. The operator requires outbound internet access so that we can have this communication path, but no inbound ports need to be opened. While we're in our PDS settings, let's take a look at some of the other options we can configure for our data service deployments. First, let's talk about storage options. Storage options define how the data in the Kubernetes cluster should be managed. Things like what type of file system we should use, whether our persistent volumes should be replicated to protect from failure, and what kind of provisioners should be used. Let's create one for our demo app while we're here. If we click the Add Storage option button, we will give it a descriptive name, of course. In our case, we'll call this PX BBQ, and then we'll select what type of file system should be used. After that, we can decide which provisioner we want to use when creating our persistent volumes in the cluster. And then finally, we select the replication factor for availability purposes. I'll choose a replication factor of 2 here so that I have a copy of my data on another host in our Kubernetes cluster in case a node fails. Then we click the Add button to finish that up and make it available for us when we deploy our data services. Next up, we can see our data services options. The first thing that you should know is that each data service has slightly different options that can be applied to them. So for this particular example, I'm just going to choose Elasticsearch as an example app that we can modify. Inside the data services menu, we can see that we can make changes to both the resource settings and the application configuration. So first, off to the resource settings. Resource settings are pretty simple to explain. They are the size of your data service instances. Do you want small, medium, large, or tall, grande, and venti? You choose how your sizes work and what you'll allow your end users to request from the menu. You can choose the default sizes that we provide for default installations, or you can click the Add Template button to define your own sizes. Here, you'll again give the resource setting a descriptive name, and then you can set CPU requests and limits, as well as memory requests and limits, and then finally your storage request size. When you're all done filling out the form, click the Add Template button to save your resource settings for the Elasticsearch service. Next, of course, we look at the application configuration settings. Now, application configuration settings are very specific to the data services. Each data service has different options you might want to automatically set, like heap size, or the root username, or auto-creating topics, or whatever makes sense for that type of data service. To create a new application configuration template, click the Add Template button and give it a name. Then you can click the Add button, and then you can enter one-to-many key value pairs. Don't worry if you're not sure what to add here. We have configuration options in our documentation for each of the data services. Some of them have quite a few customization options that are available to be used. In our example, I'll set a logging setting to warn, just for demonstration purposes. Then we click the Add Template button to save our application configuration settings for Elasticsearch. Going down the list here, next up is users. I'm not going to discuss this in depth, but in the administrator settings, you can also see our PDS users, so we can add and remove access for these services. Pretty common configuration for users, so let's move on to the good stuff. Now on to our backup configurations. Our data services hold actual data, so we have to protect them appropriately. We can set template options so that our data services are backed up on a regular schedule. Before we can back up our data services, we need to provide some information about where the backups should be stored. To do this, we first need to provide some credentials to our backup repo. I've set this up already so that you won't be distracted by my AWS S3 access credentials, but just to show you how to add new credentials, click the Add Backup Credential button, and then pick which type of backup repository to use. Then you can give your credentials a name and enter your username or password or access keys and secret keys before saving them. Now you wanted to specify the backup target. Again, click the Add Backup Target button. You'll select the backup credentials created in the previous step before giving the target a name. Then specify the bucket name and the AWS region before you click Add. Backups have to be taken on a schedule, so we then create a policy. You can either leave the default policies in place, or you can create a custom policy to take your backups on the cadence that you prefer. To add your own, click the Add Backup Policy button. Again, give it a descriptive name, and you can specify your cron expression for how often you want your backups taken, and specify how many old backups you want to retain. Then click Add. Thanks for sticking with me while we configured some of our settings. Now let's deploy a data service through the PDS user interface. Back to the online storefront of our data services, we can select a database that we want to deploy. For this example, we'll deploy the MongoDB Enterprise database for our Portworx BBQ demo application. When we select our data service, we'll be prompted to enter some information about our application. First, we need to decide what version of the application to deploy. Normally, we'd probably select the latest version, but I'm going to choose an older version so we can upgrade it later. Then we give our deployment a name before we select which Kubernetes cluster we want it deployed to. After you select the deployment target, then you can pick which Kubernetes namespace you want the database deployed in. You have the option to provision a Kubernetes load balancer in case you want to publish the database to resources outside of your Kubernetes cluster. In our case, this database is only accessed from other containers inside the same cluster, so we will uncheck this to save money on our cloud load balancers. Under Application Configuration, we select one of the application configurations that we set up earlier in our settings walkthrough. Then we select the resource setting, which, if you remember, defines the size of our database instances. In the next drop-down, we have to specify the number of instances to deploy. Since we want our database to be highly available, I'll choose 2 nodes, which means that MongoDB Enterprise will be deployed with a synchronous replica. In the storage options, we'll select the PX BBQ configuration that we created earlier in this demo, which makes sure we have replication factor of 2 for all our data. Finally, before deploying MongoDB, we choose a backup schedule from the settings we created earlier so that we know our data is protected. Be sure to select the backup target as well so we know where those backups are going to be stored. When you've chosen your deployment settings, click the Deploy button. The deployment will kick off and shouldn't take too long since these are containerized databases that don't have any data in them yet. But it will take a bit for the image to be downloaded to your Kubernetes nodes for that first time, and to set up that synchronous replica. While the data services are being deployed, you might see some events that are happening while the databases are deployed. Eventually, your database nodes will all be deployed and in sync, and you can start using your shiny new data service with your application. Let's put ourselves in the shoes of an application developer or app owner. So let's take a look at the very simple architecture of our demo app called Portworx BBQ. This app has a web app front end built in containers and connected to our MongoDB database. This is very similar to the monolith we discussed very early on. From our command line, let's take a look at the PX BBQ application manifest. You can see we're using some environment variables for our app to connect to its backend database. We need to provide a username, password, port, and list of nodes to connect to so that our application has a place to store data. Our application owner can go back to the PDS console and retrieve all of this information from the connection link on the MongoDB database cluster we just deployed. In the additional details screen, we can grab the database endpoints, ports, usernames, and passwords needed to connect to this cluster. We'll simply go back to our application manifest and place our username, the password, and any nodes we want to connect to, along with the port which is already set correctly. Then we save our Kubernetes deployment manifest before applying it to our Kubernetes cluster. If we run a kubectl get pods on the PX BBQ namespace, we can see not only is our application being created, but we can see those MongoDB pods that were deployed from PDS as well. If we check the logs for our PX BBQ application, we'll see that the logs state that we successfully connected to the MongoDB database with our application. The last thing we'll do is deploy an ingress rule so that our application is available to users. If we cat our ingress.yaml file, we'll find the hostname used to connect to the PX BBQ app. If we paste that URL into our web browser, we can see that Portworx BBQ application is up and running. To test out the database part of the app, let's register a new user so we can order some delicious Portworx BBQ. I'll click register and then fill out my information. My information was saved, so the database seems to be working correctly. If you look through this app, you can see that it's a website for a barbecue restaurant. And as such, we should be able to create an order. Let's submit a new order from the orders page for some smoked brisket, Brussels sprouts, French fries, and of course the pork special for a drink. The order gets submitted successfully, and if we look at our previous orders, we can pull them up, so the Mongo database is working as expected. Now that we've deployed our database, let's take a look at other tasks we can perform now that we've got a successful database deployment. One thing we might be interested in is how the data service is performing. Does it have enough resources, or is there a bottleneck of some kind? From within PDS, we can look at the metrics for this data service right from the portal. We can see file system details such as the read and write latency in milliseconds. We can see application-specific metrics like the number of active connections to the MongoDB database or the total number of documents in the database. The metrics page gives you a quick view of your running databases. We also talked earlier about backup schedules, but let's face it, sometimes we're going to make dramatic changes to our application, and we're not going to do it right after our backup schedule kicks off. Sometimes we need to take an ad hoc backup, like right now. This is simple to do. We just click the backup option for our data service and then select our backup target. PDS will begin to take an application-consistent backup of our database while we wait for it to complete. This specific backup shouldn't take too long, as we don't have much data in that database quite yet. But after a few moments, we should see our backup was created successfully and listed in our backup jobs list. If you remember when we deployed MongoDB Enterprise, we chose to deploy an older version of MongoDB for our deployment. Our security team just mentioned to me that this was a big mistake, so we need to upgrade it. Not to worry, we can select the update link from the MongoDB and simply select the update button for the latest version of MongoDB. Portworx Data Services will begin a rolling upgrade of the MongoDB database so that both nodes are not offline at the same time, leaving our Portworx BBQ app running while we perform the upgrade. You'll see some of the MongoDB nodes go down while the node is being upgraded to the latest version. You'll also see events happening in the user interface while this rolling upgrade happens, similar to the ones shown when MongoDB database was deployed initially. Eventually, both nodes will come back online and have a green status with the latest version of MongoDB being deployed for you. Pretty simple upgrade process here. The last day 2 operation we'll perform on PX BBQ is to scale it. I noticed during our metrics review that we could use another instance of MongoDB in our cluster. To scale our MongoDB instance, we'll simply click the Edit link in the UI. You'll notice that we can change both the resource settings to a different size, which effectively scales up our database, or we can modify the number of nodes for our cluster, which is scaling out our database. Either option should work and will take place in the background. Since I updated the number of nodes to 3, you'll see some familiar events happen in the UI, as well as another node being deployed. At this point, you may be thinking, wow, this is kind of neat, but I don't want to deploy all these databases by hand each time. There must be a way to automate all of this, right? Well, right you are. The tasks we just walked through in the GUI are all possible through our API. In my profile, I can create a new user API key. This gives us a way to authenticate with the API with our user credentials. Give the key a name and an expiration date because we know we don't want keys sitting around without being rotated frequently. Then to test out the API, we can copy our key and go to the Swagger UI, which is available to all PDS users. We can click the Authorize button and paste in our API key from before, and then click Authorize. Great, we're logged in using our API key. Now from the Swagger UI, we can look through all of the API calls we're allowed to make. Swagger will help us decide what parameters we need and what will be returned. Since we logged in, we can even use the Swagger UI to make API calls for us. For example, here I'll execute a GET operation on the Accounts API. Swagger will return actual data about my instance in the Swagger UI. This makes it easy to build scripts for application management and deployments. So let's use the API to deploy a more advanced application. Here's another app called PX Delivery. PX Delivery is another demo application that's used to order food from places like PX BBQ and have it delivered to your home. You can see from this architectural diagram that we still use MongoDB Enterprise for authentication, but we push any order submissions into a Kafka topic. Data from that Kafka topic is pulled by a Kafka consumer and pushed into a MySQL database. The PX Delivery app then reads previous orders from MySQL. This looks a lot more like those Microservices apps that we talked about early on during this demo, doesn't it? So let's pull up the PDS UI on the left side of our screen, and on the right, a shell. From the shell, I'll run a Python script that makes API calls to PDS to deploy all 3 of the data services we need to run the application. The script outputs the deployment IDs to standard output, and then waits for the applications to become active before finally creating a Kubernetes secret with the connection strings needed to connect to them. You can see in the PDS UI that our data services are showing up like we could expect, and eventually the script will complete successfully after the resources are up and have provided connection information. Once my deployment of data services has completed, we'll run a Helm command to deploy the PX Delivery application, which will mount our projected secrets and read their information into environment variables. The app then uses these environment variables as part of the connection strings. I'll check the app to see if the pods are running, and it looks like PX Delivery is up and ready to go. I'll now split my terminal window so we can see logs for both the PX Delivery app and the Kafka consumer pod that we will run to pull data from a Kafka topic and push the data into MySQL. If I run some kubectl logs on the pods, you'll see that connections look to be working. So let's pull open the PX Delivery URL in a web browser and test out the microservices-based app. The web page came up, so let's try to register a new user. I'll go ahead and enter in a first name and a last name, the email address, and a very secure password, along with, of course, my delivery address, which is critical for PX Delivery to actually deliver my orders to my residents. When I finally hit the submit button, it tells me that I successfully registered. And in the logs, you can see that we pushed some data to MongoDB, which is a good sign that our Mongo database is working correctly. Now to test Kafka and MySQL, we need to submit a food order. So let's go to the orders page, and we'll choose Portworx BBQ as the restaurant we want to order from. I really enjoyed the smoked brisket last time, so let's get that again, but we'll pick some new sides, and of course the pork special to drink. Then place our order. When we do that, our order number is sent to us, and in the logs we can see that the order was saved in Kafka. And our Kafka consumer in the bottom terminal has found a new entry in our Kafka topic. The consumer grabs the entry and pushes it into our MySQL database. Once that order has been processed and added to MySQL, it should show up in our order history in the PX Delivery application. This means all three of our data services that we deployed through the PDS API are working with our application. Pretty slick. That's it. We used the Portworx Data Services UI to deploy a simple application with a single database, backed it up, upgraded it, scaled it, and looked through its metrics. Then we used the PDS API to deploy a more complicated application with 3 data services to show how easy it is to build on top of PDS for your CI/CD based workflows. I really appreciate you spending time learning about PDS, and I'd love to see you for future videos. But right now, I've got some barbecue that's getting delivered. Thanks for your time.